Okay, let's talk about the spectrum of laser light. So we have seen that in a resonator, at least there are two mirrors. Let me draw one over here. So these might be the mirrors of your resonator, and this is your gain medium or the amplifier medium. So the light is going back and forth through this medium and just gets amplified at a certain frequency or frequency range. So what we call over here is the spectrum is that, let me explain first this picture over here. So what you see over here is this curved line represents the bandwidth of the amplifier, and what I mean by bandwidth is, since this horizontal line over here represents the frequency, and these are the modes, the frequency modes or resonator modes for this 2-meter resonator. That means only the frequencies with this and this and this values will get amplified inside this between the two mirrors, and the other frequencies will not get amplified. But this is not the only condition, that in order to have a certain frequency for the laser to be lased, we also must have this bandwidth, this line exceeds this dashed line, which is called the loss line. You see over here a dashed line, and this dashed line represents the loss inside this resonator or the laser medium, or the two mirrors. These are the mirrors, right? So what I mean by loss is that supposing that you have a kind of certain intensity of light inside the between these two mirrors, after a while, if this intensity decreases, then there is loss. That means at least we must have this for even for a working laser, in order to have the intensity of the light get out of this the region between the two mirrors. That means get out of the some of the lasing light toward out of the box, out of the resonator. We must have at least one mirror which has less than 100% reflectivity. Some of the light must go through, so that even this is a loss. And this loss line, if this loss line is above the bandwidth, this is this line, this curved line, that means your laser is not going to laze, because there is no gain, no amplification inside, no net amplification. I mean, this corresponds to the case that the number of atoms in the higher energy level, let's say this is 3, let's say N3, and this is N2, which is a low level. In order to have this condition to be satisfied, we must have this bandwidth curved line above this threshold, the dashed line. And sometimes this is equal to 1 minus R. R is the reflectivity of one of the mirrors, supposing that the other mirror is 100% reflective, and this is 1 minus R. Or it is also equal to loss. Loss is equal to transmitted light through this mirror, which is not a coupling mirror. Let's usually this mirror is called the coupling mirror. Coupling mirror is the mirror that the laser light goes through. So, I mean, theoretically, this loss is equal to the transmission through this mirror, plus you see over here is letter A, the capital A, representing the absorbance. Okay, of course, this is the case that some of the light can get absorbed by the medium also. So, or even some of the light can be absorbed by the mirror. Not all light ideally passes through or reflects back from a mirror, but sometimes the mirror itself absorbs. Even this is a very small value. When also there is another absorption source, is that the medium, that the gain medium is sometimes absorbs light. So That's what this dashed line represents. And as I said, in order to have this laser works, we must have this curved bandwidth line above this dashed line. Okay, and let's look at the following slide. Over here, what you see is that you see in this case we have this curved line, which is the bandwidth of the amplifier. At least some portion of this curved line stays above the dashed line. That means between the frequency between this and this range, from here to here, all the frequencies will get amplified. Okay, so when you look at this projection of the bandwidth to the frequency axis, you know, we see these resonant frequencies, that is, you know, potentially the frequency of the laser modes between these two mirrors. Only one of them, which is this one, is projected over here, which has the gain larger than the loss line. That means this frequency will be amplified. And when you look at the other frequencies, this frequency, for example, since even there is no any bandwidth line over this frequency will not get amplified, and also similarly this one will not get amplified. Even the potentially these two resonant frequencies are the laser modes between these two mirrors. This specifically, and this laser will not laze on this frequency or this frequency, but this frequency. Why? Because this frequency is just, you know, under the gain bandwidth, which has a net gain of this much. Let me draw over here. And this frequency is just has this much gain. Okay, this is the amount of gain, because this portion is just stays above the dashed line. Okay, this part is just the, you know, the amount of amplification that this resonant frequency will get. Well, sometimes we may have that this bandwidth, okay, this bandwidth of the amplifier is so large that it amplifies not only one frequency, but also in this picture, this frequency and this frequency will get amplified. So why do we think that, for example, this particular frequency will get amplified? Because if you draw a line just above it, you see just crossing the loss line above, this much of gain is provided to this frequency so that it can get amplified through these two mirrors. So this is amplified. Well, similarly, this one, okay, this one also, when it is projected, has this portion, okay, this portion of gain provided by the bandwidth of the amplifier. But you see, these gains, this much and this much, relatively smaller gain in compared to this center frequency. This is the gain provided by this amplifier for this specific frequency or mode of the laser. So in this case, since all these three frequencies will get amplified, although not all of them will get the same amount of amplification, as you see over here, this and this and this, somehow these are representing the intensity of these lasing modes, and the center frequency will get the largest intensity, but this other two frequencies will get relatively small intensity when you operate this laser. And the laser will become having three oscillating frequencies, which has net gain. So this laser will have three colors. right? Because the frequencies are three frequencies are getting amplification, and so we will see three different colors. Although these frequencies are very close to each other, I mean, you will not differentiate these colors by your eye. The colors will be very very close to each other. For example, if this is red, this is going to be a little darker red, and this is going to be a little lighter red, but it's all going to be red, because the frequencies are very very much closer to each other. So that's the case. I mean, that's what about this. This is what the loss line about. Okay, when you see these picture, this is what you understand.